So let's move on to expanding each logarithm if possible. And this is using the properties that I'm about to write up here on the screen. These properties here are the properties that you can use to expand or compress logarithms. And it involves the concepts that we've seen in the past, where if you have two logarithms with the same base, all these involve the same base. If you're adding, you can take the two terms and multiply them. If you're subtracting, you can take the two terms and divide. If you have a constant out front, it can become an exponent to the inside piece. So this wants us to expand. So we have log base 5, and then it has 3 squared divided by x. So I'm first going to do this. I'm going to do log base 5 of 3 squared minus, because division corresponds with subtraction, log base 5 of x. And then I can move that 2 out front. So this would be 2 log base 5 of 3 subtract log base 5 of x. This one here, there's 3 terms. There's 15, an x, and a y. So I'm going to need 3 logarithms for when I expand it. And since all those terms are multiplying, that means I'll be using addition. So one of them's log base 3 of 15, another one's log base 3 of x, and the other one's log base 3 of y. This one here, I've got 3 terms. There's no base, so it's an invisible 10. So this would be log 8 plus log x plus log z to the 4th. And then I can move that 4 out front to get this. All right. This one wants us to contract them, put them back into us all into one piece. So I've got log. I see a subtraction sign, so I know I'll be using division. The 2 and the 4 are linked by addition, so 2 times 4 is 8. The 7 was paired up with this negative sign, so it's going to go in the denominator. This one would be log base 3. And what I can do is put this 5 with the y. I see a subtraction sign, so I know I'll need division. I'll have the y down there, because it was with the subtraction sign, into the 5th power. And then up top is the 2x, because it was a plus sign, so it will go on top of the fraction as the numerator. Here, I'm going to go ahead and move the constant out front up as the exponents first. And then we're going to put it all into one logarithm, invisible base 10. The ones that have plus signs go as the numerator. And that z, which is paired up with a subtraction sign, goes in the denominator. So those properties, you don't really do anything with them except when we're just practicing them, except moving things around all into one package or breaking it up into as many pieces as you can. We do use these to help us solve equations, and that's why we practice them. Solve each equation, and you'll see that our x is up in the exponent. Now, we learned a couple different ways on how to solve this in this chapter. One of which would be, if we are looking at this equation, recognizing that these can both be expressed as base 2, because 8 is 2 to the 3rd power, and 32 is 2 to the 5th power. And then we could set the exponents equal, because we had the same base on both sides. And then when we divide both sides by 6, we'll get that x is equal to 5 over 6. You can use that method anytime things can be expressed as the same base. And all of these different ones here can be done like that. But we also learned a way that can work no matter what, even if they're same base or not same base, on something like this. Like if I gave you 2 to the x is equal to 7, to where 7 can't be expressed as a power of 2. We learned a method that can solve no matter what. If you like doing it this way, and you recognize that the scenario is appropriate for it, you can certainly do it. The other way, though, is to use drop, log, and roll, to where you drop your base, this would be log base 8, and you roll these two. So log base 8 of 32 is equal to 2x. Now, in order to get x by itself, I need to divide by 2. And if you typed in log base 8 of 32 and you divided it by 2, you'd get a decimal. But then if you hit math enter, you would recognize that you get the exact same answer of 5 over 6. And I would encourage you to practice on your calculator typing that in. Type in your log base 8 of 32, and then when you get that and you divide it by 2 and you hit math enter, you should get that 5 over 6. If you're not getting that 5/6, you are typing in something wrong here, and that's an issue. Because if you're going to use this method, the drop, log, and roll method, you need to be able to type these in on the calculator appropriately to get your fraction answer. So this one here, we could use drop, log, and roll. So this would be log base 7, 343 is equal to n. That's just a simple type in now. There's no more division I need to do. So if we do log base 7, 343, we get the answer is just a 3. And that should make sense, because if you think about what logarithms are really asking, this is asking 7 to what power gives me 343, and the answer to that is 3. And 3 also makes sense right here because 7 cubed is equal to 343. So one more time here, we'll use drop, log, and roll. If you type in log base 9 of 27 on your calculator, and then divide it by 2, so if you type this in correctly, you should get the answer of x equals 3/4. All of these could have been done with the same base method. This one, for example, we could have called it 3 squared. 27 is 3 cubed. Now when I set the exponents equal, and I divide both sides by 4, you'll see we get the same answer. So you can use either one of those methods when both sides of the equation can be expressed as the same base. So let's solve the equations where x is trapped inside the logarithm. And this is where we're going to need loop and swoop, which is where we take our base, even if it's invisible, we raise it to the other side, and then set it equal to the end of the arrow, the swoop part. So here we'd have 100 is equal to x minus 25, and when I add 25 to both sides, we'll get that x is equal to 125. And you could check this by pushing the log button on your calculator. So if you push the log button on your calculator, and you type in 125 minus 25 and you hit enter, your calculator will tell you 2. This next one, before we do loop and swoop, we do have to have everything as isolated as possible. So we get this, and then now we're ready for a loop and swoop, to where we'd have 10 squared is equal to 2x plus 5. So that's a 100. And when we subtract a 5 from both sides and divide by a 2, we'll get that x is equal to 95 over 2. one final one here. We'll divide both sides by 3. And we'll do a loop and swoop. And all these were base 10. If the base was something different, you would just raise it to whatever the swoop power is. So we have 100. We'd subtract a 1 from both sides. And we get our final answer of x equals 99/2. These are still going to require loop and swoop, but before we're able to do that, we're going to need to use our properties of logarithms. To where this one is going to condense to one logarithm, but using division. And then now we're ready for the loop and swoop. So we have 10 cubed is equal to x over 4. So that would be 1,000. And when I multiply both sides by 4, we'll get that x is equal to 4,000. So it's the same concepts of above. So we'll get this here. We'll get 10 to the negative 2 power equal to x over 4. So that's 1 over 100. When I multiply both sides by 4 here, what we'll end up getting is 4 over 100, which would simplify to 1 over 25. One final one here. Now this time I'm not able to divide by 2 because then I'd have to divide by 2 here. So that's not going to be an option for us. What will have to happen on one like this instead is we can go ahead and condense them and move this 2 up with the x. So it'll be x squared divided by 4 is equal to 2. So we'll have 10 squared is equal to x squared over 4. So here we'll have 100 is equal to x squared over 4. And when we multiply both sides by 4, we get that x squared is equal to 400. I'll square root both sides to get that x is equal to plus or minus 20. Now, what we need to check for is see if anything is extraneous. So you have to use the original equation on this. So we're not going to use this guy because that was after we changed it some. If you go back into the original equation and we try to substitute in both positive and negative 20, negative 20 won't work right here. You can't take the log of a negative number. And remember, that is because the graphs look like this. So we can't have any negative x values because the graph doesn't reach that, which means the only answer on this is the positive one. So x is equal to a positive 20. Suppose you deposit $2,500 in a savings account that pays you 5% interest per year. Wants us to figure out how many years will it take your money to double? How many years will it take for your account to reach 8,000? So what we'll want on this is to use this equation. So our initial amount is $2,500. We get a savings account interest of 5%, which is 0.05. So here's the equation we want. For part A, if we wanted it to double, that means our 5,000 would be our y, because it's double 2,500. This is an example of where we have a variable in the exponent, and this is why we've been learning about logarithms, because we can use it to figure out how long it would take our money to double. The first step on this is to get it ready for a drop, log, and roll. Right, and there's the double. That 2 represents that doubling. And so now we're ready for the drop, log, and roll. So I'll have log base 1.05 of 2 is equal to the time. So that's just a value we can type in on the calculator. If you want to use, I haven't shown it for a little bit on this video, if you wanted to use the old fashion of doing it, you would do log base 10 of 2 divided by log base 10 of 1.05. You can also just use your calculator's alpha window, option 5, which is log base. Either way, when you do these, you should get a time of about 14.2 years. So that's how long it would take to double. Now, part B wanted us to figure out how many years would it take to get to 8,000. And the process will be very similar. We'd first need to divide both sides by 2,500. And we get 3.2. So that means you'd want your money to be 3.2 times as large if you're going from 2,500 to 8,000. And then we'll use drop, log, and roll again. So log 1.05 to the 3.2 is equal to t. So if we type that in, log base 1.05 of 3.2, we get that the time for that type of growth would take about 23.8 years. Now, the reason we have logarithms as a function is because if you wanted to do this for different amounts over and over again, you could actually just make a graph. If you graph log base 1.05 of x, you could then look up all sorts of amounts of, if you wanted your money to quadruple, you could then look in your table and figure out what the y is. If you wanted your money to be multiplied by 10, to where how long would it take to have $25,000, you could graph that, look at your table, and quickly fill in that information. And that's what logarithms do. They help us answer investing questions such as this. So this is write each expression as a single natural logarithm. And natural logarithms is invisible base e. And that way we don't have to write the e, we can have a different format, and that format is ln. So this would still be the same properties as previous. If you have subtraction, you're using division. So that one's really just natural log of 2. This one, I can put the 3 as the exponent. And then we also have the 9. And if I wanted to do this without a calculator quickly, I could think of the 9 as 3 squared, and then use same base, add the exponents. So this would be 3 to the 5th power, or you could just type in 3 cubed times 9, and you'd get the same answer of 243. For this one, the a can become the exponent. So we'd have 4 to the a, and since we're using subtraction, that means we'll use division with the b. So this one's just to solve each equation, but we have to understand that our base on all of these are invisible e's. And then we'll get things ready for our loop and swoop. So this would be negative 1/2. So when I do my loop and swoop, I'd have e to the negative 1/2 power is equal to x. A lot of times we'll leave our answer just like that. This is asking us, though, to find it as a decimal. So that would be x is approximately 0.61. And remember on your calculator to find E is above the division button. So you have to hit second division button to get the E. And then you can raise it to the -1/2 power. This one, I'll need to divide both sides by 2. And then now we're ready for a loop and swoop, where E is our base. So don't be intimidated by E. It's just a number that just sits there and waits for us to type it into the calculator. So for this one, we'd have E to the 7/2 plus 4 is equal to 3x. And when we divide both sides by 3, we'll get that x is equal to E to the 7/2 power plus 4, all divided by 3. Now, when you go to type that in on your calculator, you will want to do the numerator first. So if you do E to the 7/2 power plus 4, now there's a couple ways that you could do it on your calculator. If you hit alpha y equals and you're on the newer calculators, you can hit option 1 and it'll give you a fraction where you can type in the numerator and denominator. You could also just type it in on your calculator to where the numerator is in parentheses and then divide it by 3 like that. Whichever way you do, you should get that x is approximately 12.4. One last one here. You need to get it ready for loop and swoop. We have our invisible base E. So E to the -6/5 power is equal to 4x minus 6. I could add 6 to both sides and then divide by 4. And we get that x is equal to E to the -6/5 plus 6 all over 4. And you need to use the same method over here to type this in on your calculator. You know, I typically just go ahead and type in my numerator in parentheses and then divide it like that. But when we type this answer in, we should get that x is approximately, so I'm typing mine in right now, 1.58. Now, one more thing that I didn't type out onto the review is that we do need to be equipped to use drop, log, and roll when our base is E. So if I gave us E to the 2x is equal to 7, we would need to use drop, log, and roll, but since our base is E, I'd use natural log and roll. So then we could simply divide both sides by 2, and we'd have that x is equal to the natural log of 7/2. And that's a button on your calculator. Natural log is the third button up. It says ln on it. And you could do ln of 7 divided by 2, and you get approximately 1.25. So these work the exact same way, except we just have to use natural logs. So for example, if I gave us 4e to the x minus 1 is equal to 11, we'd first divide by 4, and then we'd do a natural log and roll to where we'd have ln of 11/4 is equal to x minus 1. We could add 1 onto both sides to get that x is equal to the natural log of 11/4 plus 1. And you could type that in on your calculator to get the decimal approximation. It would be 2.01.